So we've learned about the universe on its largest scales, and we found out that most of the universe is energy that's part of space itself. And there's also things like dark matter, some mysterious material that's 30% of the universe that is gravity. And then there are the things like stars. They make up less than 1% of the universe. And our planet, which I regard as probably the most important thing in the universe, at least to me, well, the Earth is 1/1,000,000th of the mass of our sun. And so we have to figure out why something as insignificant as our Earth really came into being. It's a really challenging question, how something so small can be made out of something so big.
Yes, so planets in the overall scheme of the universe are almost irrelevant, but they're important to us because we live on one. In this lesson, we're going to talk about how you turn the primordial gas into the planets and the sun, the solar system. We know the process starts with giant molecular clouds and ends up with planets. The overall picture is fairly well understood, but there's a whole bunch of gaps in there, different steps along the route that are very, very obscure. And this is what we're going to highlight as the unsolved mysteries of solar system formation. But anyway, the whole process starts with giant molecular clouds.
And giant molecular clouds are some of the building blocks, we know, of solar systems. And here we see the Trifid Nebula, a place where there's large amounts of hydrogen and helium and dust, and all coming together to form the solar systems of the future.
Where do these giant molecular clouds come from? Well, you get gas and stars. Some of the stars explode. As they explode, they squirt out enriched gas, as we talked about in the first Light in the Universe lesson. This gas coalesces to form another generation of stars. Some of these in turn explode, squirting out yet more gas. All the time you've got clouds of primordial gas left over from the Big Bang raining down. So giant molecular clouds are sort of like the scum that forms from all these different processes coming on. You've got gas blasting this way, gas blasting that way, gas falling in, swirling around. So it's no surprise these are not nice spherical symmetric shapes. They look pretty chaotic.
But they are beautiful. And indeed, some of the prettiest things in the sky. For example, here we see the Orion Nebula, which is one of the nearest places in the sky where this whole process has taken place, where the giant molecular clouds have come together, formed a whole bunch of stars, which you can see here in the center, and presumably lots of systems as well. And Orion is not unique. There's all sorts of interesting things in the sky. This nebula, the Eagle Nebula, is seen with the Hubble Space Telescope, or, for example, the Lagoon Nebula. These are all some of the most interesting things to look at in the sky, and are all sort of the aftermath of this process of making stars and solar systems.
So these giant molecular clouds are very tenuous, they're very big, often light years in size. We have to turn them into something like this, a sun and a planet. And that's a very difficult challenge, because planets, like our own here, are very, very much smaller. This is only a few thousand kilometres across. So you've got to turn something from light years big to only a few thousand kilometres across. You also need to condense the elements. The giant molecular cloud is mostly made of hydrogen and helium, whereas at least the inner planets in our solar system, not any hydrogen or helium to be seen there. We're looking at silicon, magnesium, oxygen, rocks. There are some planets, like the gas giants, Saturn and Jupiter, which are mostly hydrogen and helium. But even in these ones, the fraction of other elements is much higher than it is in the giant molecular cloud. So we seem to need to do two things. We need to shrink these clouds by an enormous factor, and we need to concentrate elements other than hydrogen and helium. To figure out how our solar system formed, we're going to need some clues. And there are a number of clues in the current structure of our solar system which are really important here. Let's start off with two great clues: the size of our solar system and the relative size of the sun and the planets. We often see pictures of our solar system showing the planets close to the sun. These are almost never done to scale. They all show the planets far too close to the sun, because otherwise it's just a bunch of dots on acres of paper. What does the solar system look like on a real scale? To get a sense of how big the solar system is and how much empty space there is in it, let's have a scale model. As our scale, imagine the Earth is this size, the size of this ball. To that scale, the Moon would be the size of a tennis ball, about 10 meters away. Jupiter would be the size of a major office building on that hill. Pluto would be about twice as far away as this mountain. That's the solar system. To get to the nearest other solar system, Alpha Centauri, you'd have to go 25 times around the world. On the same scale, if the Earth is the size of a basketball, the Sun is the size of a large building. There are some more clues as to how our solar system formed in the orbits of the planets around the Sun. If you just put a whole bunch of random planets in random positions and give them kicks, they will end up probably in orbits like these, some going forwards, some going backwards, and generally very elliptical orbits where they come really close and whip around and then come back out again.
Looks like it's going to be a bit of a train wreck over 1 billion years, Paul.
Yes. So this is what you'd get if you just put planets randomly near stars. What we actually see in the solar system is something rather different. This may look like a perfect circle, but it's actually the path of the Earth around the Sun.
It really is almost a perfect circle. So if you put an overlay of a perfect circle, which you can pretty much not even see the difference.
Yes, so if you just about see this, maybe if you look really hard, there's a perfect circle overlay there, and it really doesn't look very different. It is an elliptical orbit, it's not quite a circle, but it's close as damn it to being a circle. And the same thing applies to the other planets, at least in the inner solar system. Here are the inner ones, their orbits over the next few years, and you can see they're all going in the same direction around the Sun. None of them are going backwards.
Yep.
And they're all in pretty close to circles. You can see Mercury is a little bit off-centre, and likewise for Mars, but they're actually pretty damn close to nice and circular orbits.
But that's a very convenient traffic pattern compared to the first diagram you showed us.
Yes, indeed, not by coincidence. If you look edge on, here's what you see. They're all going pretty much in the same plane.
Now, interestingly enough, that doesn't look like it's going to help traffic. That looks like it's going to be against the, will help collisions occur.
Yes, you think it would be safer if some things are tilted one way, some the other way, but actually they're all going in the same plane. If you look at the solar system from edge on, everything's in the same plane. This plane is called the ecliptic. Not absolutely the same, but pretty damn close.
Yes, so
that's a big clue.
Seems like we have a bunch of clues here, exactly.
If you look at the outer solar system, once again you're seeing the same sort of pattern. Things are going around in the same direction, pretty much in circular orbits.
We're not going to wait here for Neptune to finish, are we?
No.
Okay.
So here are our clues. Virtually all the mass is in the Sun.
And it's spread out over 10 to the 12 meters, so it has a certain scale.
Orbits are pretty damn near circular.
And everything's going around in the same direction.
And in the same plane, the ecliptic plane. So any theory of solar system formation has to explain these facts.